Okay, so today we will start a new chapter on polynomial interpolation. You have already used in several courses interpolation. For example, if you have taken the thermodynamics course, you have seen that if I have a table and I want to interpolate the value of entropy or enthalpy at a certain temperature, I need to do interpolation. Okay, we have several ways to do interpolations. We will introduce this one of the common ways in this chapter. The objectives of this chapter is to learn how to use the Newton and Lagrange interpolation polynomials to any order, and you will understand that higher order polynomials can be oscillative. So as we mentioned in the introduction of this chapter, interpolation has a lot of applications. One of them is if I have a thermodynamic table here, for example, and I want to compute at a certain temperature what will be the entropy, the enthalpy, the internal energy, etc. I can do this by just interpolating between the two values. So if I want to know at 135 what is happening, I can do linear interpolation. So I consider that the variation between 400. So for example, if I want to interpolate for, let's say, the enthalpy, H, okay? I just write for T equal 400, H equal to 1224.6, and for H equal to 450, the value is 1251.4. So if I want to assess what will be H for 435, I can consider that the variation of H is linear in this interval. And then I can say that the slope is constant. So I can write that H minus 1251. I can use the slope here, for example, or between 435 and 450, or between 435 and 400. So because the slope is the same, so to obtain the slope, you need 2 points. If I select these 2 points, the slope will be equal to H minus 1251.4. Or if I choose the 400 point, I will take 1224.6. And if I select to use these 2 points, then I will do H minus 1251.4 over 435. Since I considered the second point here, so minus 450. So 435 minus 450, okay, equals to the slope given by these 2 points. So it will be equal to, if I consider points 450 and 400, I will have that the slope is 1251.4 minus 1224.6 over 450 minus 400, which is 50. And by doing this equality, I consider that the variation is linear between these 2 points, and I am able to get the value of H. And we can do several types of interpolation. We can do quadratic interpolation. So if we take 3 points instead of 2, etc., we will introduce these methods in this chapter. Another important application of interpolation is, for example, calculation of a volume. So let's say we want to know reserves in oil. We know that we have oil in this part of, let's say, under the earth. And we want to determine what is the corresponding volume of oil that we can extract. So if we just have data on several points, so here, if we count them, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. You have, let's say, 15 by 15 points. So in total, you have 225 points. Okay, and this number is not enough to know to have a very exact function. So if I want to draw a function that is more smooth, I want to have more points. So I can extrapolate I can interpolate, sorry, between points, so that I can draw a curve that has has a smoother profile with more points, and this will allow me to calculate then the volume under this function, let's say. Another application is in photography. So you know, in photography, higher the number of points you have, better will be your result, and higher will be your resolution. So if you consider, let's say, the following image, and we do zoom, you do a zoom on the image. If you consider then the first image, you don't take a lot of points. In the second image, you take several points more. So when you take higher number of points, you can have a better resolution. So in all these examples, it is of advantage for us to do interpolation, because when we do interpolation, we'll be able to have a better accuracy. Okay. Now, how to do these interpolations? We have several methods. So to start with, let us consider the following example here. You have the white curve represents for you an actual curve. And you have a true curve represented in white, and you want to find the extrapolation for this curve. Now, you just have 3 points here, okay? And you want to model a white curve. If you just do interpolation between the 3 points, you will get the following green curve. The green curve is a quadratic curve, okay? So if I just know 3 points of the white curve here, and I am interested to know what will happen after these points, I don't have the choice to do interpolation, because to do interpolation, I need a point. I need points here. If I don't have points here, I am forced to do extrapolation to be able to determine what will be the value, an approximation of the value. Okay, and then this is, as you can see in this figure, it's not very accurate. This is why we don't recommend to do extrapolation unless we don't have the choice. So if we don't have another choice, it's fine, we can do it. But we might have large errors, especially as you can see if we are very far. If you are close here to this point, the extrapolation might work better. But if you are very far, you begin to have very large errors. Okay, so in general, it's advised to use interpolation, not extrapolation. Why we say inter? This means that the points where you want to interpolate is between your points. And here you have these 3 points. You define this interval. Any point in between, when you find any point in between by the green curve, this is interpolation of the value of the function. And as you can see, the error here is acceptable. You don't have large errors when you do interpolation, while for extrapolation, you might have large errors. So, for example, if we go back to this example, how we can have extrapolation? Let's say you have only this table, and you want to find at 350 Fahrenheit what is happening, what is your enthalpy, or what is in your entropy. Then you have to extrapolate. You say, I will consider that 350 is a part, so I consider the linear interpolation between 360 and 400, and consider that 350 belongs to this line. Or if I have here, for example, 2050, also same procedure, I will consider that I will find the linear interpolation here, and say I will extrapolate my linear result to find what is h at 250. Okay? But if you have the choice, you don't do it. You do it only if you have in a table, for example, in this table, if you have what is at temperature 340, for example, what is the values of entropy, enthalpy, internal energy, etc. You don't need to extrapolate. You just do interpolation. Let me check your questions. Oh, okay. Okay. Now, let us compare interpolation and regression. So in previous chapters, 14, 15, we have introduced regression techniques, okay, which consider of finding a fit that minimizes error. What is the main difference between interpolation and regression? First, in regression, your fit doesn't have to pass by any data point. You can have a fit that is not passing by any of the data you use. For example, let's say like this. Let's say you found this is so for example like this. Let's say this is the linear fit. The linear fit is not passing by any of the data point, but it is minimizing the total error. However, here, when you do interpolation, then your curve should pass by the 2 points, or if you do a quadratic fit, it should pass by the 3 points, etc. So this is why in interpolation we don't have any error at the data points, because my function will pass by these data points. So no error here. But on the other hand, we will have error in between. So it will, of course, the error here, the summation, if you want, of errors will be higher than the error in this case, because in this case we minimize the error. Okay, we did a minimum possible error to have a function passing by all of these points. So if we consider then interpolation, so in general also interpolation will work if you want to do linear interpolation, you should have 2 points. In case you want to do quadratic interpolation, you should have 3 points, which is not the case in regression. In regression, you can have a lot of points and do a linear fit. So also in concept, it's different. Okay. Now, this is why here, when we define interpolation, at data points, there will not be error. But as you can see here, so for example, when you consider, let's say, these 3 points, you will have error for any point in between. So no error here, 0 error here, 0 error here, 0 error here. But in between, I have error. Okay. Now, what are the main interpolation techniques? First, the method we introduced now that you are familiar with here, basic polynomial interpolation, which consists on considering that I can, depending on the number of data I have, I can come up with a polynomial that is passing through these points, these data points. So, for example, if I have, as we said, if I have 2 points, I can do interpolation, a linear interpolation. If I have 3 points, I can do a quadratic interpolation. If I have 4 points, I can do cubic interpolation, etc. So we can say that if we want to perform a polynomial interpolation to the power n minus 1, okay, then I need to define n unknowns, because for any polynomial, if it's power xn minus 1, you have n coefficients, which are p1, p2, until pn, because you have one coefficient for x power 0, and then so you have 1 for 0, one coefficient for x power 0, one coefficient for x power 1, until one coefficient for power n minus 1. So in total, the number of coefficients needed is equal to n. And higher is the order of your polynomial, higher will be your unknowns, and higher the number of data points you should have. So for example here, if I have an interval and I want to perform in this interval a linear interpolation, then I need 2 data points, okay, as we have seen in the table together. Now, if you have in this thermodynamic tables, if you wish to do, instead of linear interpolation, if you wish to do a quadratic interpolation, then you can say, let me take 3 points here. 450, 500, 550, let's say. I know that I want to interpolate, for example, the enthalpy. So I take these 3 data points and I define a polynomial function between these 3. Therefore, if I have any value between 450 and 550, and I can use this interpolation, the quadratic interpolation, then, to find what is h. Okay, so it can be done. You can do several interpolations, linear, quadratic. Usually in such tables we do linear interpolation, but this does not mean that it's wrong if you do another type of interpolation. So now what will change is the number of unknowns. If I want to do a quadratic interpolation, I need 3 points, and I have 3 unknown coefficients, P1, P2, and P3. And if I want to do a cubic interpolation, then I have 4 coefficients that are unknown, P1, P2, P3, P4. So here it's P4. And I need to do, if you want, I need to take 4 data points to be able to solve for my P1, P2, P3, P4. Now here in the solution of these coefficients, we can go back to our previous chapters to solve a linear system of equations. So you can summarize this linear system of equation by writing it in a matrix form, where matrix A will be, let us try together to see why this is the form of the matrix. Let us take a simple example, the case of 2 points. So if I have 2 data points, x1, y1, x2, y2, and we want to find what are the corresponding coefficients P1, P2. Okay, so how we find P1, P2? We say that the our linear fit should pass by these 2 points. So first, the first equation I can write is that P1 x1 plus P2 equals to y1, and for the second, to pass by the second point, the second equation will be P1 x2 plus P2 equals to y2. Now you can transform this system into a system of linear equations. So you have your matrix will be, so this is a 2 equations, 2 unknowns. I can transform it to matrix form. So I can write that the first column represents the coefficients of P1, because my unknown, what is my variables? P1, P2. Okay, these are the I want to solve for P1 and P2, so it's the x vector. So this is P1, P2. Now, the first column of A will constitute the coefficient of P1. So as you can see here, it's x1, x2. And the second column represents the coefficient of P2, which is 1, 1, equals to the result vector, which is y1, y2. Okay, so now this is the form of my matrix A and B for the case of 2 points. This means a linear fit. Okay, now what if I have several points? We can repeat this. Let's say if you have 3 data points, okay, x3, y3, what will change now? I will have P1, P2, P3 here, y1, y2, y3. And to know what will be this matrix of coefficients, I should write the linear equations. So let us do it for 3 points, data points, and then we will deduce for a general number of points what will be the form of the matrix. So if we do it for 3 data points, then I will have that the first equation should be, so now we have P1, P2, P3, okay? And P3 is the coefficient of x0, so this multiplies x0. P2 is the coefficient of x1, and P1 is the coefficient of x squared. So your first equation will be P1 times x1 squared plus P2 times x1 plus P3 equals to y1. Your second equation will be P1 times now x2 square plus p2 times x2 plus p3 equals y2. Just let me check your questions. No, George, the degree of the interpolating curve will be the number of points minus 1. And if you have a linear interpolation, you need 2 points. If you have a quadratic interpolations, you need 3 points. So always the degree of interpolation will be the number of points minus 1. Okay. And now the third equation will be P1, so I'll write it here. P1 x1 x3 square plus P2 x3 plus P3 equals to y3. Now if I want to put it in matrix form, what will be my matrix of coefficients? So the first column is coefficients multiplying P1. So the first element will be x1 squared. The second element will be x2 squared. The third element will be x3 squared. So x1 squared, x2 squared, and x3 squared. Now, for coefficients of P2, I have x1, x2, x3. So here I will have x1, x2, x3. And always for the final coefficient اللي هو multiply x0 هيكونوا 1 1 1. So the last column will be 1 1 1. Okay. And then I will generalize this result to say that if I have n data points to solve for the n coefficients, this will be my matrix. I will start by, so the first, if you want, the first column will be the column multiplying P1. It is x1 to the power n minus 1. So if I'm, as we give the example here, when it was a cubic fit, okay, we started here by x1 square, x2 square, x3 square. Okay, so now, for example, if you have, in the case you have, let's say, a cubic, so we did the quadratic fit together now. We have a cubic fit. So if we have to do x cubed, okay, when we have to do a cubic interpolation, then the number of points needed will be 4, because always, as we said, the number of data points is 3 here plus 1. It should be larger than, it should be 1 more than the degree of the function. So I will need 4 data points to find to do a cubic interpolation. And then the first column, okay, will be x1 to the power 3, okay, x2 to the power 3, x3 to the power 3, and x4 to the power 3. And then I will complete, my other elements will be, if this is x1 cube, the second, in the same row, you will have x1 square, then x1, then 1. And if this is x2 cube, in the same row, you will have x2 square, x2, and 1. So always, you in the same row, you start by, for example, if you start by the first row, this is all for x1. So x1 power n minus 1, which is here 4 minus 1, 3. And you continue to decrease the degree until reaching 1. And now, if n equal 4, this will be 3, this will be 2, this will be 1, and the last is x to the power 0, which is 1, etc. So for any number of data points, you will be able to fill your matrix of coefficients here. And you can get P1, P2 until Pn. You can get n unknowns. And of course, to solve such system, you have already several techniques. You have iterative techniques. If you recall last chapters, you have Gauss-Seidel and Jacobi methods. If you want to use numerical methods, you can use Gauss elimination. You can use U factorization. You can use the inverse of the matrix. All of these can help you to find your coefficients. Okay. Now, what is the problem with this method? The problem with this method is that this matrix is highly ill-conditioned. And higher is n, it will be more ill-conditioned. And we have seen that if we can avoid working with ill-conditioned matrix, it will be better. Because here larger is n, larger will be the degree of illness, and larger will be the round of errors involved when calculating our coefficients. Okay, this is why this approach, even if it's used, is not very recommended. And if you want to be, especially, it's not recommended for high order polynomial interpolation. So in general, in engineering courses, you use this method for linear or maximum quadratic interpolation, but you don't use it for very large n. Okay, so this is why we will develop in this chapter other new techniques that can perform operations of interpolation without inducing large round of errors, which are Newton method and Lagrange method. So now we will introduce the first new method for interpolation, which is Newton interpolation. And this technique will just change the form of expression of the polynomial. So instead of writing it as p1x to the power n minus 1 plus p2x to the power n minus 2 until plus pn, it will just change the form of the function. And for example, if you want to perform a linear interpolation, which should pass through x1, y1, x2, y2, then we will write the function in this way. f1x equals to b1, a coefficient b1, plus a coefficient b2 times x minus x1. When we write it in this form, what will be b1? If we set the condition that when x equal to x1, f1 of x1 equals to y1, then we find that b1 will be equal to y1. So if we write it in this form, b1 will be equal to y1. And in order to compute b2 is computed from putting the condition that when x is equal to x2, f1 x2 is equal to y2. And y2 is b1 plus b2 times x2 minus x1. Okay? Now how we can write b2? b2 is written as f of x2 x1. So it's y2 minus y1 over x2 minus x1. Because here, just if you rearrange, you will get that b2 is y2 minus b1, and b1 is y1. So it's y2 minus y1 over x2 minus x1. This term, we call it, this is the slope, okay? In the linear interpolation, it's the slope. This is called the first finite divided difference. And we define it as f x2 x1. So when you read f x2 x1, this means that you do y2 minus y1 over x2 minus x. Now, what is positive here about Newton interpolation? That, for example, if you start by a linear interpolation, and then you decide to proceed with a quadratic interpolation, b1 and b2 will not change. You know why? Because now, when you want to write a quadratic expression, you will have y equal to b1 plus b2 times x minus x1, plus just you will add to it b times b3 times x minus x1 times x minus x2. Why we do this? And why in this case b1 and b2 will remain unchanged and just we will add a new coefficient b3? Because if you define the function in this way, now for x equal x1, this term is 0 and this term is 0, so b1 will remain equal to y1. When x is equal to x2, this term x minus x2 will cancel out, and you will go back to the same relation that y2 is equal to b1 plus b2 x2 times x1. So you only have to determine a new coefficient b3, and b3 is determined by setting f of x3 equal to y3. Okay, so now what will happen is that when we define for quadratic interpolation the following form, so you can conclude what is the general form. Start by b1, b2 times x minus the x of the first point, x1, plus, so here when you have 2, you just do x minus x1. When you have b3, you do x times x minus x1 times x minus x2. If you want now to do a cubic interpolation, you will add the following. You will add b4 times x minus x1 times x minus x2 times x minus x3. Okay? And you will proceed. And then b1, b2, b3 will remain as they are, and now just b4 will change. But of course, what is the condition? I'm taking the same data points, just I'm adding new points to them in the same order. You will understand more what I am saying when we do an example. Okay? So remember that b1 and b2 remained unchanged, but I should not change points 1 and 2. So data points 1, 2 should remain the same. When I do quadratic interpolation, I add a third point to them, a new point. And then when I find 1, 2, 3, I keep data points 1, 2, 3 as they are, and I add a fourth data point, 4, etc. This way I can increase the order of my interpolation. Okay. So now, how to find B3? So as we said, B1, B2 will remain as they are. What about B3? To find B3, all I have to do is to write the condition that for x equals to x3, y3 is equal to f2 of x3. So if I replace x3 by its value in this formula, so I get that y3 should be equal to b1 plus b2 times x3 minus x1 plus b3 times x3 minus x1 times x3 minus x2. And now, what I should do, I just should rearrange my terms and replace b1, b2 by their expressions. So we have seen together that b1 is y1 and b2 is y2 minus y1 over x2 minus x1. So now, let us rearrange terms together. We want to find value of B3. So B3 is equal to Y3 minus Y1 minus Y2 minus Y1 over X2 minus X1 times X3 minus X1 and the whole term is divided by what is multiplying B3, which is X3 minus X1 times X3 minus X2. Okay, so now if I rearrange a little bit my terms, what I will obtain? I will obtain the following, that if I divide, look, I have here X3 minus X1, okay? So what I can do is I can say, if I divide here the following term, so I want to obtain this, look, X3 minus X1 will simplify, so here we have Y2 minus Y1 over X2 minus X1 We can divide each term of these by what is given. So let me put it here because it's not very, we don't have a lot of space here. It will not be clear. Let me do it for you here on a white screen. Look, this meeting